Billions of years ago, our solar system was just a giant cloud. This cloud was called the primordial cloud. It was made up of gas and dust, floating in space. The cloud was very cold. It was also very dark. The gas and dust were spread out over a huge area. This cloud was the beginning of everything we know. It was the birthplace of our sun, our Earth, and our entire solar system.
Not too far away from the cloud, a star died. This star was much bigger than our sun. When it died, it exploded. This explosion is called a supernova. Supernovas are some of the brightest events in the universe. They release enormous amounts of energy. The supernova sent shock waves through space. These shock waves hit the primordial cloud and squeezed it together.
As the cloud was squeezed, it started to collapse. It became smaller and denser. It also started to spin faster and faster, like a figure skater pulling in their arms. The spinning motion flattened the cloud into a disk. This disk is called the protoplanetary disk. It was like a giant spinning pancake of gas and dust. In the center of the disk, the material clumped together. This clump became hotter and denser. It was the beginning of our sun.
The clump at the center of the disk kept growing. This was no ordinary clump, it was the heart of what would become our sun. In the vast expanse of space, a dense cloud of gas and dust began to coalesce, pulled together by the force of gravity. Over millions of years, this cloud continued to collapse under its own weight, forming a spinning disk with a dense core at its center. As it grew, its gravity became stronger. The gravitational pull of this growing mass was immense, drawing in more and more material from the surrounding cloud. This process of accretion caused the core to become even denser and hotter. The gravitational forces at play were so powerful that they began to shape the very fabric of space around the forming star. This strong gravity pulled in more and more gas and dust. The material spiraled inward, feeding the growing core. As the core accumulated more mass, the pressure and temperature at its center continued to rise. The intense gravitational forces caused the gas and dust to compress, heating up to extreme temperatures. The pressure and temperature at the center became incredibly high. At the heart of this growing mass, conditions were becoming extreme. The temperature soared to millions of degrees, and the pressure was immense. These conditions were necessary for the next critical phase in the birth of a star. Eventually, it was so hot and dense that nuclear fusion began. This was the moment of ignition. The intense heat and pressure caused hydrogen atoms to collide and fuse together, forming helium. This process of nuclear fusion released a tremendous amount of energy, creating a brilliant burst of light and heat. Hydrogen atoms fused together to form helium, releasing a tremendous amount of energy. Our sun was born. This energy radiated outward, lighting up the surrounding space. The sun, now a massive ball of burning gas, began to shine brightly, marking the birth of a new star. It became a giant ball of burning gas, giving off light and heat. The sun's surface was a roiling sea of plasma, with solar flares and eruptions sending streams of charged particles into space. This radiant energy would become the lifeblood of our solar system, providing the heat and light necessary for life on Earth. This marked the beginning of our solar system as we know it. The sun's gravitational pull began to shape the orbits of the surrounding material, forming planets, moons, and other celestial bodies. Over billions of years, this process would lead to the formation of the diverse and dynamic solar system we inhabit today. The birth of the sun was not just the creation of a star, but the dawn of a new cosmic era.
Section 5 planets take shape. While the sun was forming, the rest of the protoplanetary disk was also changing. The gas and dust in the disk started to clump together too. These clumps collided with each other, sticking together and growing bigger. Over millions of years, these clumps became planets. The planets were different sizes and made of different things. This depended on where they formed in the disk. Section 6. Inner planets, hot and rocky. Close to the sun, it was very hot. The heat from the sun blew away most of the lighter gases like hydrogen and helium. Only heavier materials, like rock and metal, could withstand the heat. This is why the inner planets, Mercury, Venus, Earth and Mars, are small and rocky. These planets are called terrestrial planets, meaning Earth-like because they have solid surfaces. Section 7. Outer planets, cold and gaseous. Farther away from the sun, it was much colder. The lighter gases didn't get blown away. They clumped together to form giant gas planets: Jupiter, Saturn, Uranus, and Neptune. These gas giants are much larger than the inner planets. They are mostly made of hydrogen and helium, like the sun.
Section 8. Our solar system today. Our solar system today consists of the Sun at the center, orbited by 8 planets. The Sun, a massive ball of burning gases, primarily hydrogen and helium, provides the necessary heat and light to sustain life on Earth. It is the gravitational anchor for all the planets, dwarf planets, moons, and other celestial bodies in our solar system. The inner 4 planets, Mercury, Venus, Earth and Mars, are rocky and terrestrial. These planets have solid, rocky surfaces with mountains, valleys, and, in some cases, active volcanoes. They are composed mainly of silicate rocks and metals. The outer 4 planets, Jupiter, Saturn, Uranus, and Neptune, are gas giants. These planets are much larger and are composed mostly of hydrogen and helium, with thick atmospheres and no solid surface. Jupiter and Saturn are known for their extensive ring systems, while Uranus and Neptune are often referred to as ice giants due to their icy compositions. Between Mars and Jupiter is the asteroid belt, a region populated by remnants of the early solar system. This belt contains millions of rocky bodies, ranging in size from tiny pebbles to dwarf planets like Ceres. These asteroids are thought to be leftover building materials from the formation of the solar system that never coalesced into a planet due to Jupiter's strong gravitational influence. Beyond Neptune lies the Kuiper belt, a region of icy bodies, including Pluto. The Kuiper belt is similar to the asteroid belt, but is far larger and more massive. It contains many small, icy objects, including dwarf planets like Pluto, Haumea, and Makemake. These objects are composed largely of frozen volatiles, such as methane, ammonia, and water. The Kuiper belt is also the source of many short-period comets that we see in the inner solar system. Our solar system is constantly moving and evolving. The planets orbit the Sun in elliptical paths, and their positions change continuously. This dynamic system is influenced by gravitational interactions between the planets, moons, and other celestial bodies. Over millions of years, these interactions can lead to significant changes in the orbits and rotations of the planets. The planets orbit the Sun, and the Sun itself moves through the Milky Way galaxy. Our solar system is located in the Orion arm of the Milky Way, a spiral galaxy with billions of stars. As the Sun orbits the center of the Milky Way, it takes about 250 million years to complete one revolution. This journey through the galaxy exposes our solar system to different cosmic environments, which can influence the conditions on the planets and the overall structure of the solar system.
Section 9. The future of our solar system. The future of our solar system is determined by the Sun. The Sun, a massive ball of burning gases, is the heart of our solar system. It provides the necessary heat and light that sustains life on Earth and governs the orbits of all the planets. But like all stars, the Sun has a life cycle, and it won't last forever. In billions of years, the Sun will run out of fuel. This process is slow and gradual, taking place over an immense timescale. As the Sun exhausts its hydrogen fuel, it will begin to burn helium, leading to dramatic changes in its structure and behavior. As it dies, it will expand into a red giant star, engulfing the inner planets, including Earth. This transformation will be catastrophic for any remaining life on our planet. The Sun's outer layers will swell, and its surface will cool, turning it into a massive, luminous red giant. The intense heat and radiation will strip away the atmospheres of the inner planets, rendering them uninhabitable. Eventually, the Sun will shed its outer layers, leaving behind a white dwarf star. This white dwarf will be a dense, hot core, roughly the size of Earth, but with a mass comparable to the Sun. It will no longer produce energy through nuclear fusion, but will instead slowly cool and fade over billions of years. The outer planets may survive, but they will be altered by the Sun's death. The gravitational dynamics of the solar system will change, potentially causing the outer planets to shift in their orbits. These planets, including gas giants like Jupiter and Saturn, may experience changes in their atmospheres and temperatures as the Sun's influence wanes. Our solar system, born from a cloud of gas and dust, will eventually fade away. The remnants of the Sun's outer layers will form a planetary nebula, a beautiful but transient structure that will disperse over time. The once vibrant solar system will become a quiet, dark place, with only the faint glow of the white dwarf remaining. But its legacy will live on in the remnants it leaves behind. The materials ejected by the dying sun will enrich the interstellar medium, contributing to the formation of new stars and planets. In this way, the death of our sun will give rise to new beginnings elsewhere in the galaxy, continuing the cycle of stellar evolution that has shaped the universe for billions of years.